What's up, guys, and welcome to this video on the final question of the 2018 final exam. Okay, so we're doing question 9 on photons and electrons. Okay, so the graph shows the maximum kinetic energy EK of electrons emitted from a surface of calcium metal, which varies with frequency of the incident radiation. Cool, so we've got EK and we've got F. So this point here would be F naught. Okay, so if we start off with the definition, nice easy marks. Define the work function. Okay, so the work function is the minimum, is the minimum amount of energy needed to emit an electron from the surface of a metal. Okay, so that is what the definition is, and we get 2 marks. Cool stuff. Then we have 9.1.2. It says calculate the work function. Okay, and like I said, we know what F naught is. F naught, we can say, is roughly equal to about, I'd say that point there is 6.8, so let's say 6.9 or 6,9 times 10 to the 14 hertz. Okay, times 10 to the 14 is because of that. And we get, okay, so once we have F naught, we can use the formula. Let's see if I've got it open. There we go. Where is it? Looking at photons and electrons, the last row, middle column. Okay, so then we can say that the work function is equal to H times F naught, where H is Planck's constant. So we know what Planck's constant is. It's 6,6 times 10 to the minus 34 times F naught, which is 6,9 times 10 to the 14. And we get the work function is equal to 4,55 times 10 to the minus 19, and the units are joules. Okay, and there we go, we get 4 marks. Okay, so the last question says 9.1.3, the experiment is repeated using magnesium instead of calcium metal. The work function of magnesium is 1.3 times the work function of calcium. Draw a second graph. Okay, so draw a second graph. Okay, so first of all, let's work out what its work function or frequency is. So the frequency of, what is this, calcium is equal to 1,3 times the frequency, which was 6,9 times 10 to the 14. Okay, and that comes out as roughly 9 times 10 to the 14 hertz. Okay, so that gives us the x-intercept, or yeah, the x-intercept. So it's going to be right there. And then we know that the gradient of this graph is equal to Planck's constant, right? So that is a constant. So the gradient for both of these graphs is going to be the same. So let's see if I can draw it relatively. There we go. That looks pretty. Basically, those are parallel to each other. Okay, don't draw in the parallel. This is just because my line isn't so straight and I didn't use a ruler, but they are parallel to each other. Okay, and we get 2 marks for that. Okay, so question 9.2. The 4 emission lines P, Q, R, and S in the hydrogen spectrum are illustrated in the diagram. Okay, so we have a nice diagram, and we've been given P, and we've been given the emission line and the wavelengths. Okay, the frequencies associated with these wavelengths are emitted when electrons move from a higher energy level to the minus 3.4 electron volt energy level. Okay, so question 9.2.1 says calculate the value of the energy of the light associated with the emission line S. Okay, so with the emission line S, so we're with this value right here. So we want to know the energy. So we can use the formula E is equal to hc over wavelength, or lambda. Okay, h again is Planck's constant, which we know is 6,6 times 10 to the minus 34. C is the speed of light, which is equal to 3 times 10 to the 8. And lambda is going to be 6,58 times 10 to the minus 7. Okay, and when we plug this into our calculator, we get a value of 3,0 times 10 to the minus 19 joules. Okay, and we get 4 marks for that. Question 9.2.2, which emission line is produced by the transition from the highest energy level to the minus 3.4 electron volt energy level? Briefly explain. Okay, so for this we need to understand a relationship. So this is mostly a theory question. So what we can say is that the wavelength lambda, okay, so we can say the wavelength is inversely proportional to the energy difference. Okay, so what does this also mean? This means that the wavelength is directly proportional to 1 over change in the energy level. Okay, so if we want the highest change in E, therefore the highest change in energy level, so let's say, therefore the highest change in E would be from the smallest wavelength. Okay, and which wavelength is the smallest? This wavelength right there. So that would be P. So therefore, line P basically is your final answer. And we should get 3 marks there. Then it says, question 9.2.3, state why knowledge of emission line wavelengths is useful to scientists to identify substances. Okay, so basically emission lines, again a theory question. So emission lines are unique to each element. So each element will have a different emission line, so we can use it to identify the substances. Therefore, they can be used to identify unknown substances. Okay, and so those 2 last questions are basically theory questions. And that is the end of the paper. Okay, cool guys. So thanks for watching. I hope you found, so we've gone through the entire paper and I hope you guys found it useful. In the next video, I will probably be doing a different paper. So yeah.